the how to do design of components using a standardized handbook. So I think from Satya you learned that things are not standardized in India, but at least you can understand and appreciate. Is it better? Okay. Understand and appreciate standardizing things, right? In terms of how things can work out. So I'll show you how a standardized product work in terms of, one of the things I left, I was appreciative of what you're doing in the last hour is that I talked about some of these things yesterday from how things have to come together. So you're showing how the design is done. So PCI puts out this handbook. It's for the industry, and everything is standardized in this one. So this is an older version of it. Let's see if I can go. So they go through. So I think between Professor Amal and myself, we kind of talked about, along with Professor Surya, general precast prestressed concrete. So precast is a key piece of the puzzle. You probably heard from different presentations, right? The prestressing steel gives a lot of benefits and flexibility. The handbook then goes through, I'm still figuring out access to this document. If I can find the site, I'll share with all of you to get the link so that you can at least look at an older version of it. So I want you to understand, from there they go to the preliminary design. So that's the reason I ask you a question. Once you decide the building dimensions, how do you size the members, right? The handbook is very useful in terms of helping you decide what type of, we talked briefly about that yesterday. I want to go a little bit deeper into it. We talked about analysis and design yesterday. Then they have what they call a design of precast prestressed concrete components. After that, you can see, I think Satya covered product handling and erection bracing, a design of connections, which I will spend more time. And then they also now integrated precast architectural. I think you asked about fire. Now they have incorporated fire as well as an element in the handbook as to what you need to do to prevent any containing fire, or how the design should be done so that fire issues can be tackled as well. What I want to show you is typical members that you see in this one. I'll go through a little bit more in detail. So let's see, that's XTEM. So here's the hollow core panels, how they have standardized it. So they have a section at the top here, which tells you 76S. 7 is a number of strands, so each strand is what we talked about as a pre-stressing wire, and then how many numbers that you're using. So that 7 is basically spread across the depth of the section. You could see here. The second, number 6, is a diameter, so 6/16 is the diameter they specify. So in the US, because they use imperial unit, once they go below 1 inches, it goes to 1/2 inch, 1/4 inch, then 1/8, and then 1/16. So 6 means 6/16 is the diameter of the strand. S implies it's a straight strand. Typically in a hollow core, that's what you would be using it. These are 4 foot wide panels, so that's standardized. The width is standardized, so everybody can produce a 4 foot panel. You could see there's a depth specified. So in this case is 6 plus 2, 8 inches, so it's roughly about 200 millimeters. The width is 4 feet, meaning about 1.2 meters wide. Then they provide the properties of this particular section. Now, what the table gives you is, on the top they give you a span length. So the width is fixed at 4 feet. So if you have a 20 feet wide span or bay, you need to have 5 of those elements. That's an obvious one. But then the length of the span in the other direction is given on the top. So you already decided based on the dimension of your building. So you will pick, so let's pick a number. So let's say it's a 25 feet span is what you're looking for. The 66S we've already gone through. So 66S is basically tells you that it's going to be 6 strands of 6/16 diameter straight tendon. What they give you here number at 25 is, so if you focus on that 52 is the amount of superimposed service load or live load you can add on top of it. So if you're doing preliminary design, you have these numbers. So you can look at the number and say, you know, your number is maybe 45 or 40, so that 52 is going to work for you. Then they have 2 other numbers given. One is a camper, I think, superimposed live load. Let's see, one is a camber. What is the other one? Dead load. Yeah, so that's provided here. So one is an estimated, so first number is an estimated camber in erection in terms of inches. So you already have a feel for how much camber you're going to have when you start the construction of the building. The second one is both are camber. One is a short term and the other one is a long term camber. So you could see as soon as I looked at this number, 25.4, so this is a 52 inches. If this doesn't work for me, I'll go to 65, I can go to 88, depending on the superimposed live load or service load that you're looking for. So in terms of design, once you decide your number of bays and the footprint of the structure, you could throw these things and create your structure pretty quickly. That's a huge advantage. So let's say they designed this for 76S. So if I go back here, 76S, and that's a particular hollow core, which is designated as 4HC6. Let's say a project requires 80 slabs and I'm on a critical path, I can't produce 80 of them within a time span. They just call around and say, who can produce this particular slab so that they can improve they can meet the deadline. So that's how the timeline I mentioned yesterday is met, because anytime you don't meet the timeline, that they get penalized. So when you do your own job, everything is in-house. There's an advantage, you can move things around on your own. But when other people are coming in, you have to have accountability, and they get penalized if you don't make that happen. So this standard is get used for almost every product. So this is a hollow core slab. So you can see so many of the different varieties depending on the type of structure, span length. You could pick and choose what you want to do. So you can see how wide these sections go. Let me go to the next one is a beam, I believe. Oh, they have a solid flat slab. So in case somebody wants to have a solid flat slab, same thing goes. So the second and third row basically gives you the short term as well as the long term camber for that particular structure. And then once you know the dead load, you can pick which one to use. Okay, so here's the beam designation. So beam designation is, you can say it's a 12RB16. So the first number is, I believe, let's see, I think it's the width of the beam. So B is what is defined here. So you can see all of them are here 12. After that it goes to 16, so 16-inch wide beam. The H is the second number, so that's designated here as the last 2 digit. 16, 20, 24, so that define what those beam sizes are. Again, they provide the same thing. They give you the safe superimposed service load. So you don't need to do any calculation, basically, when you pick these numbers. So it's just picking things from a catalog and figure out, if I'm going to use only walls and hollow core, or frame and hollow core, or double T, I can just put the building together based on this handbook. And then they decide, okay, how do I achieve that construction? I said, I could handle it, or do I only have capacity for the floors? I need to team up with somebody else to do beams and columns, and then they go to them. But nobody else, like if they happen to have a project where for some reason they want to do something longer, different, then they will have to talk to the precast. It's not that they're going to ignore it, but they have to make specialized formwork. So typically, I think I mentioned yesterday, the precaster would use steel formwork. The double hollow core, for example, I showed how the positioning of the strands are. They're all fixed in the plant. So you don't move things around for construction to construction. You can pick and choose whether you only use 4 foot wide or you're going to go maybe 2 meter wide. They could make those changes, but typically those are all standardized. The standardization actually help you with cutting the cost down because the formwork cost is minimized. So they buy a formwork, they'll keep the formwork for 20, 30 years, right? I presume that's the case here. Steel formwork also improve quality. They can also heat, like thermal curing, they could do all of those things. Some of these beds, I presume you also have, the bed itself can be, used to be, they can vibrate the bed to consolidate concrete. So all of that comes with it. You can see all of that attributes towards ensuring good quality concrete as well. And especially cast in place is, in the US, is very expensive because the labor is expensive also. And when it comes to this particular construction, the cost is very competitive because they de-skill they call it de-skilling the labor, right? So they will have different crew, as I mentioned. So somebody is tying reinforcement, you train them once, they will just tie reinforcement forever, right? So they don't have to do other stuff. That's their responsibility. Occasionally what they will do is, if they don't have jobs, first choice would be they produce standardized products. They will have a track record of what is being sold most. So if it's a 4 foot wide, 25 feet core slab, this hollow core slab is the one getting used mostly, they will just produce and just keep them in the yard. They know somebody will come someday and ask for this, which is very common. So they don't idle the troops, or they don't like change their schedule. Every day is the same for when it comes to construction contractors. They will work on it. I think Satya also touched on, so there are two type of beams that get heavily used, especially with hollow core and double T's. One is an L beam. So they have standardized the L beam because I think we talked about, cracking, torsional effects. So all of that have been done and figured out what would be the dimension, how it should be detailed, how much reinforcement to put in. So it's not just, this is a dimension, but it actually provides what reinforcement to use inside also. You don't take that and use it for yourself directly. That's what it's called preliminary design. They evaluate, they get everything together, then they go through and do proper checking, which I will just go through, which is same as what you have done for regular reinforced or pre-stressed concrete. You use that knowledge to make sure that the sections that you pick are going to work for you. Same thing. So the first 20 here is the width at the bottom of the L beam, or where this will be used for an end of the structure. The last 2 digit stands for the depth of the beam. So H is what the last 2 digits is. So if you say 20 LB24 is basically saying 20 inches wide L beam with a 24-inch depth. They're giving you the properties, so you don't have to calculate, and then they will give you the same information based on how many strands are used in the beam itself. So once you decide, not only automated here, the draftsman already has all of the beam details stored as different files. So to provide information, they'll just pull the files and put that together. So you can see how fast they can move. They don't have to keep, so only modification they will have to make is if there's any special requirement asked by the designer, they will modify those ones. So they don't sit down and draw each and every beam because everything is already there. So it's a huge advantage, especially if the industry is going to grow, to standardize based on, as I said, one of the challenges with the US is, I think we talked about yesterday about using imperial units, right? But countries like Canada, Australia, New Zealand, they all standardize. They increase in the use of precast, but it's slow though in most countries. So this is what they call an inverted T-beam. So this is, I think I've seen in Satya's one of the slide, a picture of, so where you have beams coming on both sides, or floor slab coming on both sides. So same designation. So it's the width of the beam and the height, and the IT stand for inverted T. So if you're mixing and matching different things, the camber is an important component because the camber is going to decide how much camber you're going to have during construction. It has to work in both directions, right? So you can, again, if you run into issues, you could always change the different beams to match so that you don't run into this problem. So imagine you have to do the entire calculation by yourself. You have to do everything in each direction, make sure that you have the right dimensions, and then you have to check for compatibility. With this, you can just look at the numbers and say, okay, it's going to work. If you're within plus minus, 3 millimeter, 4 millimeters, no big deal. We should be able to adjust that. So that's an inverted T. So these are for column sections. These are typically what's called the gravity columns. They provide for these columns, they provide the moment axial load interaction diagram. So you could typically, based on what your axial load requirements are and what your moment requirement is, they will tell you what the F prime C that you should be targeting for this column if you're going to use that size. If that doesn't work for you, you can go to the bigger size. So this is showing you 16 by 16 inch square columns with the 4 strands. And the second one shows 18 by 18 inch square inch with 8-inch strands. And so anything that, as I said, wants to go something bigger, you can certainly go. So this is 2024. For some reason that you decide that, for some specific requirement that you have to have 22-inch beam, where the numbers are going to be roughly. You can figure it out based on these by interpolation, and then you can detail those columns and they will be able to accommodate those things. So even though if they use steel forms, it's easy to insert some foam liner inside to reduce the dimensions. I presume you guys do the same thing. So it doesn't have to be perfectly the dimension that's in the catalog. It's sometimes cheaper to go a size bigger and just use it, but if it's absolutely requires, the precasters can easily accommodate those things. So I just wanted you to understand and appreciate the benefit of having a standardized catalog that people can use, every precaster can use. It will take some kind of a coming together of industry members deciding what would be the best thing to move forward. One of the things, I've been going to the Precast Concrete Institute conventions for several years. When they come together, the goal there, the discussion, they have committees and all that stuff. The goal is about how can we be competitive? What is it we should do to the industry to go? That attitude has to come, right, among people. They don't argue about, this is going to help you, it's not going to help me. They look at it's going to be good for the industry. That makes sense. And majority kind of rules. But I think that coalition, once they come together, then they are focused on the industry. It's not about, so the PCI makes sure that the industry members are profitable, right? So that's something that they do. But the members in turn come together and help move the agenda in terms of how do we standardize and move forward on various sectors. I think they probably have some other sections as well. So this is so it says hollow core and sandwich panels. So these are symmetric sections. So it can be used as a wall panel, or it can be used as a hollow core section if you want it, right? Again, you decided that you want to take this section, so this form is available, but for some reason you want to, you choose not to put strands on the top, then it's up to you to do the evaluation and make sure that there won't be any cracking and the camber is something that you can tolerate. That's all on you. So it's not, doesn't mandate, you cannot file a lawsuit against it. It's a handbook. You can use it or you don't have to use it. But there's huge advantage in using it. And they update this document every 3 years. So what they do is, I think I talked about blast and fire. Blast has been a pretty, in the recent time it has become more important, partly because US blasts everybody, I guess. So what they have done is they form a committee, they come together with some consensus, they ran some tests, made some recommendations, and then they will develop a guide document. Then that gets distributed, people try to use the guide document, then it will come as an appendix in the handbook. And once the appendix is basically, okay, here's some knowledge coming up. You may want to use this if you are looking at the specific topic area. And then the next version, I believe the 9th version, the appendix will move into the main section, right? So it doesn't happen overnight, but it's a process that they undertake. And there's no way that an individual company can do all of that, right? That's what the challenge is. Sometimes some of the research projects will require pretty significant investment. PCI takes a chance. Once it's for the benefit of the industry, sometimes they would put in $30,000, $40,000 I've seen, or getting $20,000 is not going to be easy. But if it becomes an important problem, they will throw $1 million, $2 million as well. Because they know that the money is going to come. The members will pay the dues, and so they know it's coming. So they will just take a loan or whatever, they figure it out. There's also some changes coming in the US in terms of how academics are doing research. I would think that it will trickle down. It's partly coming from the Trump administration. So the fundamental research that we've been doing, the NSF, for example, is known for doing very basic research. They don't look at how people are going to use or how it's going to impact. So what we are seeing is that there's more and more effort put in now to change a significant amount of the research to be more impactful in a shorter duration. And so in that sense, what they are looking for is a partnership between industry and academic, so that industry is integrated into it, and they will be able to utilize the information, and they are feeding in right from the beginning. There are advantages and disadvantages, right? Like sometimes you need to leave the scientists alone to do whatever you want to do. There's so many things got invented accidentally. But here it's all very intentional, but it's okay to go cyclic, right? So there's quite a bit of investment is being made for this industry partnership with academics, and even they are right now looking at funding PhD students who would be employed by the company but work on a PhD research that would be benefiting a company but with the university as well. So there's some changes coming up. It'll be interesting to see. So country, I think like Germany does that. They think the impact is faster, and somebody in the current administration is pushing for it. So I think I briefly touched on this. This is all pile sections. You can go into the details. So this is mostly driven by the axial load capacity. Let's see what what they provide here is the allowable service load for pre-stressed concrete piles. So allowable service load basically is what the table provide. It also provides the properties, and then obviously the allowable service load will increase if you increase the prime C. As you can see in the handbook, as I mentioned, they go up to 70 megapascal. 70 megapascal is not a difficult task for a precaster to achieve. If you're going to go beyond that, then you have to do the calculations again. And if you look at each of the rows, they look at the square pile, for example, solid section versus the 11, 12, 13. So those ones are, I believe, defining the diameter of the section in the middle. The octagonal piles, round piles. So deciding those things are pretty straightforward. So that's something I want you to understand, how easy it would be to do the preliminary design if you have a standardized document. I don't know whether in-house you guys do something like that, looking at what has been done in the past versus how you would do like an initial design of a precast components.
For preliminary, we will take this one.
You do the.
We will take this
one. But you use a PCI handbook or you use a PCI?
There's no other handbook available.
Okay. So I didn't realize that you use that. Okay.
One second good thing is Singapore handbook is there.
Okay.
But this is more elaborate.
Yeah. Okay. I didn't realize that you use the handbook here directly.
But Singapore is not speaking about standardization, sir. Pure design.
Yeah. No, so this is, let me just go into the design. So, how are we? Yeah, I wanted to just touch on some of the things that they expect you to do at the component. So this is at the component level. So we have picked the components, slabs and columns and piles and all that stuff. But as I said, it's a preliminary design is what you have accomplished so far. Also, I emphasized yesterday that then you have to check or do the proper design of the individual components, and then you also have to do checks for the entire structure, right? So this step basically focus on how do you do and what you need to pay attention to. I just want to be at a high level for two reasons. One is whatever you have learned for reinforced concrete design, most of it applies here as well. And then the prestressed concrete knowledge that I think Professor Ambulan touched on it will become the piece. So you have to do the prestressed concrete design class, learn or have that knowledge so you can go through these steps and make sure that this can be accomplished satisfactorily. So the structural engineering basics and theory are what we use. So analysis technique you used and things like that. What the handbook does is it does provide some additional guidance. So for example, if you're using an equivalent stress block, that equivalent stress block was originally developed for, I don't know, maybe 3 KSI concrete. So that will be 25 megapascal, 20 megapascal. That block, equivalent stress block, the effective depth value changes if you increase the strength of concrete. So they provide that information, for example. They provide guidance in terms of when to assume the member to be cracked versus uncracked in terms of using the properties. So the handbook gets into those details. Because it's concrete, the design is based on building code requirements for structural concrete. So yesterday I mentioned that the handbook is basically an overarching thing, but you still have to follow the International Building Code if you're doing the building design, and then ASC 7 for the loads, and then concrete design will be according to ACA 318. But starting from 2025, that requirement will be, instead of 318, it will be 319, which is dedicated for. So the first version of 318, 390, 320 have come out. There's still, I believe, duplication of material because if you're talking about precast members have equivalent stress block. Do you go to 380? No, it should be self-sustained within this document. So there's some of that is going on. So the committee is working to release an update. I think the next version will come out in 2031. But in between, they will release an interim version of it. So the other piece is the 320, which is on post-tension component. So if anything post-tensioning that has to come into play for connections and things like that, then that document has also need to play into it. It'll be interesting to see what happens to the handbook. Maybe a handbook will be simplified, but refer to all three documents to help people move from one document to the other. So the handbook relies on the building code requirements, so they make sure that you're complying with the 318, but they often come up with modification to improve their the industry practices, because based on what they have learned so far, what's likely to happen, especially with the bracing related issues versus erection issues and things like that. So the design phases, when you go into the design phases, obviously normally we do the service conditions as well as the strength conditions, but most importantly now you have to look at the manufacturing phase of it all the way to the erection, because you have to address the load imposed during handling, stripping, and installation, right? I think, Satya, you covered that well in terms of some of the challenges that you face. So it's all comes up because of the way now you're constructing it, right? So as a result, you have to pay attention to that and make sure that that aspect is covered adequately. So service condition as well as the strength requirements are fairly straightforward, just like what you do for reinforced concrete or any other structure. The second bullet that I emphasize here is that the precast. So I see that things differently here. So in the US or in some other countries, the designer and the precast fabricator are not necessarily the same folks. But as soon as the design is done, the precasters comes in, they do a shop drawing, they do the component design evaluation. At that process, they also make sure that the detailing, the fabrication concepts are coming together to improve quality of construction. So obviously, if you're doing everything in-house, that's easier to tackle. But when you have a bigger operation, then so the designers know that precast is going to come in and then get that going. Even if they have architectural features built into it. So that's a big thing now in the US. They're going more and more integration of architectural features. As well as installation of electrical heating system, process. It's all done just leaving access hole to even installing in place most of the pieces before the unit come to the on-site, basically. So they will have like plug points, if you like. So they will have sockets to connect the links together so that it goes from room to room or floor to floor. Those connections gets established. So everything is done. Again, they're moving in that direction. Okay, some of the things I won't spend too much time. You know this already. So the precast doesn't eliminate you satisfying equilibrium or strain compatibility. So those things you still have to do it, but the handbook provide guidance. When you use pre-stressing, obviously this is something that if you haven't done a pre-stress class, you guys make sure you take the class. So you will, and you too, you will get that knowledge, right, about how you do the pre-stressing So the pre-stressing steel has a pretty high forces, and you had to account for that in the design calculation as well. You can do proper calculation based using strain compatibility, because it does get challenging, and the code also provides some approximate values that some of the numbers are recently disputed, but I assume the code will update those numbers as well. In terms of completing the design, basically the factored moment has to be shown to be less than or equal to the design strength, and they provide the strength reduction factor based on net tensile strain. Is that what you also use right here? So here's what I mentioned about the stress block in terms of how to calculate. When the concrete strength goes up, the beta value actually reduces. And so they have provided some guidance. So this guidance is in the handbook in terms of how it should be calculated. Some of these things handbook introduces and take it to ACI, and then the ACI will integrate eventually. But now there's a more partnership between ACI and PCI. I would think that it will also become more monolithic in terms of how they communicate that information. So we talked about L-beams and inverted T's. So when you have a flanged element, then you have to make sure that you check to make sure that when you do the moment calculations, the neutral axis is whether it's within the flange or is it flange plus some part of the web. There's also some controversy over the years in terms of how the neutral axis depth should be calculated and the stress block should be computed. But again, this is not about doing research. I think you want to see what's the best knowledge out there, and this guidance will provide you as to how to compute those things. The minimum reinforcement, which is again, any flexural members have to satisfy this in terms of how much minimum reinforcement should be provided so that there's enough ductility is ensured. But I want to emphasize here is that I think you're getting a copy of the emulation type paper that we'll go through after lunch a little bit. What happens is that when you change the amount of reinforcement, or if you try to connect pieces with either additional reinforcement or couplers, the behavior of the member changes, which is often get ignored. So that's something I want to really spend some time after lunch to for you to understand very basic stuff in terms of how that should be tackled. At least you want to have some good knowledge about it, because the critical section, what you think is the critical section, will not be the same the moment you throw in couplers or additional reinforcement. They get used because you are establishing the connections. That's something get overlooked quite often. It doesn't cause a lot of headaches if you have a structure in a non-seismic region, because it doesn't get significant lateral loads. It doesn't get overloaded. But time and again, that issue has surfaced in the seismic regions. Then I want to touch on that, and we will do that. The modulus of rupture is, you can see, is assumed to be 7.5 root F prime C. That number is, typically people have used it. So the 7.5 is a fairly high number. Concrete can crack at 3.5, 4 root F prime C. So when you compare to that number, the 7.5 is high. The reason they use a higher number is typically the concrete strength is come out to be larger. So you may be assuming you're designing it for 30 megapascal. Precasters know they will end up with maybe 50 megapascal, right? So that factor is accounted for so that you can safely make an assumption. The key piece here is that how you would classify your member as whether it's going to be a cracked section versus uncracked section. They use that tension capacity to classified. So if you're estimating displacement or deflections and things like that, cracked versus uncracked, makes a big difference. Your stiffness can drop by 50% if it's a cracked section, depending on the amount of axial force, or if you have any axial force on the member. So in some areas or some design calculation, that becomes a critical piece. And then, as I mentioned yesterday, typically the prestressed concrete is designed to be crack-free. And so you do all of the calculation accordingly, and then, but because of your erection process, you end up causing cracking, then obviously your stiffness has dropped and there's other things will follow. Again, this is something I touched briefly yesterday, so I put in some of these things to just re-emphasize. So for prestressed concrete, you have not just service and ultimate, but you also have to look at stress limits at transfer. So when you release the pre-stressing force, especially with the pre-tension operation, into the concrete is pretty young. It hasn't matured, it hasn't gained full strength. So you could potentially crack. And that's something that you need to calculate and make sure if you're designing and you're asking a precaster or if a precaster is going to fabricate it, they will go through this calculation and make sure that member is not going to crack. So if the member is going to crack, for example, they can introduce some temporary measures to deal with that. So for example, they may put some additional strands. Again, strands are pretty cheap, kind of in the whole sense, right? I mean, it's a fair statement. They waste a lot of strands, and throwing one or two strands doesn't hurt. So sometimes they will put additional pre-stress. They may use, a good example would be they may anchor the pre-stressing strands at the end of the beam where they may have concerns. In between it will be unbonded. They may have an access point to cut that strand and release the pre-stressing. By doing that, so let's say this is a beam, they have concern it's too long until it gets to the support, and it's supported in multiple locations. They may put this temporary pre-stressing into the beam. Again, you have to check to make sure it doesn't exceed any of the stress limit at transfer or at service. You take the beam, you place it in. At that point, you can just cut the pre-stressing and release it so that the beam is now supported at multiple locations and it's not going to be cracked. Blanketing strand, I don't know, Satya, you guys use here, what they call a blanketing the strand, whether they put, so they debond it with the sheathing around the.
Actually, for end region, sometimes we used to get top reinforcement is coming at the end for taking the negative moment. We used to debond by using the plastic pipe filled with grease.
Right. Okay. So these are the tricks that precasters have, figured it out over times in terms of how to make things work. And I've interacted with a lot of precasters, and every time I go to a new plant, I'm amazed with some of the local tricks that they figured it out as to how it should be, how it should be handled for a given problem. So again, whether you're on the designer side or precaster side, you should be talking to other people in terms of, hey, here's the situation, it doesn't look like it's going to work, what do I do? They will say how it can be done. But you can do all of these tricks, but you still have to make sure the stresses are not violated in terms of what you expected to satisfy.
Sir, this allowable stress in compression. So we reduced the strength by 30%. On what factors the factors?
Extreme fiber stress you're talking about? Yeah. So what's your question?
On what factors this reduction is depends?
Why is it reduced? So typically the reduction is given for two reasons. One is obviously you don't want to go past the elastic limit, right? So concrete behavior is not remain elastic all the way to the peak. So you want to remain, the other thing is that you don't want to put too much stresses earlier on because the creep will be significant. So that's why they limit in terms of how much stress to put in. So in transfer, again, the transfer situation, if you know that load is going to be over a short time is one thing, and then you can also create micro crack in the concrete because concrete is pretty young. So when I say transfer, you're talking about 24 hours or 18 hours or old concrete. So you don't want to cause micro cracking into the concrete, and then that will compromise the quality of concrete as well.
Normally we used to do like this 0.75, we used to say like the minimum stress which is required to cut this strand is almost 70 to 75% as per Indian code. So it will match with.
Yeah. So these numbers are actually higher than what allow for like a service condition, because service condition is where the creep kicks in more. So they control that. I think it's a 45%, 0.45 of a prime C for service under service condition,
Yeah.
right? Yeah.
So normally people do these kind of things. What we are doing double set is, first of all, if suppose M40 means, we will know where the stand is going to get at what stand. In that we will take 71. As Sir said, to avoid micro crack, because the quality actually, so many reinforcement congestion will be there, it will not be perfect. So many uncertainties are there. So when we achieve points, we won't find any crack in the even the observer. So by observing, we also limit rates.
Yeah.
Even we will go for 0.6, 0.6.
Go ahead.
It is written that extreme fiber stress tension up to 7.5 per load. But in the previous slide it was again 7.5 per load. Why are the limits same in both the cases? And transfer speed should be less than
So the 7.5 is an empirical number used, but your F prime C is different now. You're not using the same F prime C. So F prime C is whatever the F prime C at transfer is what they will use, right? So again, precaster will determine actual F prime C before they release the strand, the prestressed to the concrete. So that value is what you get used. So when I say different limit state, your property should be at the respective limit state as well. And occasionally now, if it's an ultimate, they take their prime C to be 1.2, 1.3 times what's specified, because precasters do ensure higher concrete strength, and plus the concrete maturity also accounted for in that case. So again, it's a comfort level. So in the US, there's a practice that's what they say is the code specify what's required is, then there are design guides will use phrases like probable strength, that you can, what's likely to be the strength, and if you don't see any major challenges, then you're allowed to use those probable strength, right? So for example, ultimate limit state, the structure may not never see the ultimate limit state. And making this assumption doesn't cause any negative, drastic impact to the structure, then that assumption is going to be fair. So anything that you do as a designer, you should be able to defend as to why you did that, right? The prestressed transfer is the other, we talked about that, the transfer of this one. The development, hopefully you understand, so the prestressed development force, development of prestressed forces. So when you pull on at the end of the prestressed beam, you haven't released the pre-tension force into the concrete. Once it's 24 or 30 hours later, they're cutting the strands, and that's when the stress gets transferred, right? So at that point, you can imagine as soon as you cut the strands, at the end of that strand, the prestress is zero, right? Once you cut it, nothing is holding it. So if you look at the strands at the end of the beam ends, it has zero stresses. It has to come to some length to gain that full prestress. That's what I typically call as transfer length. But you could also look at that number may not be the same as what they call a development length. You familiar with the development length? I think I'm looking at these guys on concrete design. You learn development length, right? So same thing applies to the prestressing strand as well, right?
Yes, sir. 100 in India, Indian code 100.
100?
T, diameter of this.
Okay. Do you use more than 12 millimeter strands here now?
It's a 15.2.
You gone to
The
50?
strand congestion is very high. For beams and all, we'll go for 15.2.
Okay. Yeah, so you can see what numbers are being specified in the handbook. So the transfer length is given as length required to transfer prestressed force by bond, typically approximately FSC over 3 dB. You know, I didn't go into the details. Again, I'll see if I can get the handbook to you. The numbers you see here, 19, 20, 21, is actually referred to different documents where they pull the numbers. And then all of these variables are defined, so you can figure that out. Development length is required to develop, same thing what I mentioned here. Debonding guidelines, they provide debonding guidelines for the reason I mentioned, because precasters use debonding as a technique to minimize the effect of local stresses. Shear design, there's no surprise in shear design. Same process as what you do for reinforced concrete design. The only thing that you want to pay attention to it is that the pre-stress itself actually benefits shear resistance quite a bit. Two ways, right? One is it keeps the crack width lower, so the aggregate interlock is going to be better. So if you take a reinforced concrete versus pre-stress, both subjected to the same load, let's say both are going to crack, the crack within a pre-stress beam will be lower, and that's going to improve the aggregate interlock, so therefore you'll gain from it. The second benefit you get is that if you use a curved or harp tendons, the tendon itself will provide a vertical force resistance to counterbalance the shear as well. So again, those things you learn that in a pre-stress class, and I'll let you guys learn that from that particular course. The next thing I want to briefly talk about is the shear transfer and shear frictions. That's two important components important elements that comes into precast concrete, especially with how the structure is assembled, right? Satya talked about supporting beams or supporting slabs on L-beam or inverted T, for example. So when you do those supports, you have to make sure that there's a shear can be transferred from one element to the other. Shear transfer requires some kind of a mechanism, and you don't want to make it so complicated to do it. So the shear friction is relied quite a bit in terms of how much force you can transfer through shear friction. So both ACI and PCI provide guidance in terms of how one should calculate. When you do this shear friction calculation, one thing to be careful about is that if you're exercising or if you're employing different mechanisms, it depends on whether all of the mechanisms are activated simultaneously or sequentially, because you cannot double count if they are acting. So if one has to be activated or mobilized before the next mechanism can be activated, you need to pay attention to it, because both of them may not be acting simultaneously. So they make some assumption. Typically, you have a rebar going through the connections, and shear friction is not very different from what you had done for reinforced concrete in terms of how you'd calculate. In concrete courts, they are now bringing in a VC component for shear friction as well, because of aggregate interlock, which is not something that you can rely upon for precast concrete. So one of the things I want you to realize is that when you put pieces together with precast, you definitely have a section interface. It's like having a clean construction joint, right? So people try to, I think we saw in one of the slides, you have loop rebars comes together and you pour concrete. So those things intended for making them monolithic. But when the crack opens up, the crack tends to find the weaker region. typically tend to be closer to where the interface originally was. Two reasons. One is because that at the interface you don't have any tension, so it's a zero tension. If you have a dry connection, the moment you start applying loads, that's the point it's going to start opening up. So that's an obvious one. Then the rebar get mobilized, then the crack will distribute. Sometimes, again, we'll talk a little bit more, the connection details that you chose will prevent that crack to spread outside of that region. The other thing that I've done some work in the recent time is that if you look at, let me see if I can draw this. When you do precast concrete construction, so let's say you have a floor panel, wall panel. So you will have some rebar here, and you may have strands. The end regions of the concrete, if you look at, so I'm looking at something in the order of 6 millimeter, very thin layer here. They don't tend to get a lot of aggregates, because when you vibrate it, you push the smaller particles towards this. So if you're connecting this with another region, and even if you put epoxy here, let's say you put epoxy here, here's your second panel comes in, this region is still weak. So if you prevent crack opening here, the next likely place where crack develops is just adjacent to it, because it doesn't have any aggregate, so it's easy to crack. And that would be pretty visible in a structural system like that. So this is what I said the very first day, that precast has unique characteristics, unique features, and it provides some unique advantages as well. You want to take advantage of this. You don't want to make this now behave like if it's a reinforced concrete, this problem doesn't exist, because aggregate will get spread all the way, wall will be continuous. So I don't want to take this element and say, okay, let's see how I can make it work like a reinforced concrete wall. It just doesn't work. So that's something to keep in mind as well. Again, Satya touched on torsional issue. Torsional issues comes in because you are supporting beams or floor slabs on one side of the inverted T, which induce the load temporarily. So even if it's temporarily induced, if you create torsional cracks, the stiffness of that member goes down significantly. So you want to prevent that from happening. The handbook guide you in terms of when you can ignore the torsional moment. If the torsional moments stay below a threshold value, they say you can ignore it. But if it goes beyond it, then you have to provide additional reinforcement in the member. Those reinforcements are not given in the handbook as part of the standard section. That's something you should put in on top of that. Typically, you will see that comes in the form of transverse reinforcement as well as longitudinal reinforcement within the member on top of what is being recommended for service load condition. There's also a maximum limits. If you're going to have significant torsional cracks, they will basically force you to change the section. So you pick a section based on your design load using the catalog. You said, okay, this is the inverted T is going to work for me. The reason we do this calculation is so that you can go through and evaluate, am I going to have torsional, significant torsion in the beam, because that's what the precasters chose to use as an erection sequence. If it becomes a concern, then you should look at it and say, okay, how much reinforcement I need to put in? Or if you're exceeding the maximum limit, that tells you the torsional rigidity of the inverted T you choose was actually inadequate. So you have to change the section, or you have to change the erection sequence so that you don't run into this problem. So these are the problems typically precasters deal with outside of what we learned from prestressed concrete, class. let's see, what do I have? Okay, I talked about the different type of reinforcement requirement. Beam with ledges, so this is the, L beam. L beam has, so if you're supporting a beam or a slab or a floor system here, that's where the load comes in. Obviously this beam is going to be supporting the regular service load. Now you have a torsional load comes in because it's supported off-centered from the centroid of the section. And then you also need to make sure that you don't cause shear crack. So it's shown here, it's basically going from, the moment you put in load here, you have a potential to cause cracking here and shearing of this section. So that should be checked and make sure that you provide this additional adequate steel. So this steel will be there in the standard document, but it will not be there meeting your load that you're planning to apply. So that's why you need to check to make sure. So picking the standardized section is one step. Doing the design of each and every component is basically checking to make sure they will be satisfied for your case, as well as providing additional steel as needed to avoid that.
In this sketch, a bearing pad is shown. This bearing pad magnitude, I don't think Indian industry provide bearing pad.
So bearing pad is actually I will tell you the reason. Bearing pad is not. Initially the erectors told that it is very difficult to erect, but now they realize that the bearing pad single supporter will behave very smoothly. That edge crack, that outer edge is there. That edge will never crack. Mainly waterproofing is not allowing the water to come below. When I have a carbon, the top of the carbon is always undulated, micro undulation. This bearing pad will feel everything. So it is two ways. Structurally, waterproof, how we made it erected to our erectors. Bearing pad is just.
Yeah, it's a required there. So one is to make sure that there's a full contact. That's full contact between the two. So they definitely rely on bearing pads as a specification. I think my next slide is actually about bearing pad. The second thing is that they avoid stress concentration, especially if you have a DAP 10. When it sits, if you have stress concentration, you could cause localized failure. So it's a requirement that they put in bearing pads on those locations. Yeah, so this is basically the bearing and DAP 10 details. Where bearing on plain concrete would be something that you would check, but in the check you make sure that the load are distributed. There's no way you can ensure the load will be distributed unless some kind of a interface element is put in, and the simplest is to use bearing pads. If the contact is going to put much larger stresses locally, if you think of a beam is supporting at the edges of a inverted T or an L beams, then if you expect larger stresses to be generated, even if you put bearing pads, then it will be required that you strengthen that region by basically confining and increasing the strength locally. So that will be the other requirements that they will put in. The DAP 10 design is pretty detailed. So this is especially when you have a section. So this is, you're looking at so end of a say double T, for example. So this is one of the T's comes here. Here's a pad, and your inverted T one side or an L beam will be supporting it. Now this section now becomes critical in terms of this area getting sheared off. So this standard detail, there are different. So in this particular case, they use what they call a T-headed bars as well as stirrups and vertical longitudinal reinforcement. They would use, for example, bars going here with the 90-degree hooks going, so that everything is, this crack, what's shown here has to be crossed with sufficient amount of steel. So that gets, basically, someone has to check and make sure that such a failure will not take place. So again, when you design as a structural engineer, you don't pay attention unless this sequence or this particular erection sequence is something that you already recognize it. If you, for example, assume that this is going to be a rectangular section, you don't pay attention to those things. You assume how it's supported, and then based on that, you will make the evaluation. Camber, deflections, and prestress losses. Again, we touched on that briefly. Prestress losses is a huge component. I think if you're doing prestress concrete, I assume I think your homework already asking for them to assume. Yeah. So prestress losses can be as much as 20-25%, depending on the type of prestressing you do. So it's a significant amount of losses, right? I earlier mentioned that prestress take advantage of the high strength material properties, including concrete and prestressing steel. If you don't have that high strength, the losses basically will wipe out. And that was the reason why prestressing wasn't successful when initially people tried it. There are cases where people first thought of this idea, they tried to prestress it with the reinforcing bar. 3 months later, the losses basically wiped out the prestresses and the structure became ineffective. So this high strength is a huge benefit in terms of one using it for prestress, but the losses has to be accounted for. Losses has different components. The initial losses, then you have time-dependent behavior of concrete like creep and shrinkage, thermal effects. Those things will continue to have losses, so that's something you should pay attention in your calculations. You can, with the precast operations, we talk about construction, erection phase, and service limit state, and then the ultimate. The losses are different in each state. You don't have to account for the losses that's going to happen 20 years later when you do the precast erection. But you have a high amount of prestress at that time. So those are the important pieces to pay attention so that you get the right prestress to go with the right limit state in terms of when you calculate the actual losses and the corresponding stresses. So camber is basically because of eccentricity of the prestressing causing upward deflection or deflection in the opposite direction, and that should be accounted for. So you should know what the value is. So I've shown in the handbook, they actually give you some guidance as to what that value is going to be. Because if that becomes an excessive, then that has to be tackled in the construction as well. So you want to keep that minimum. So ideally, the best scenario for pre-stressed concrete or structure would be, when you're using floor slabs, beam, is to allow the camber to happen during casting. By the time service load goes in, it's going to settle, right? For gravity load, and service load is going to go down because of the deflection. So if I'm starting with an upward deflection, the ideal position would be to eliminate that camber and become flat section, right? What's the advantage of keeping it flat? You thought I want to ask you any questions. What do you think is the benefit of keeping it flat? What's that?
Oh, okay. So you can tell the deflection multiplier, it will get decreased when we go for a high strength or with steam, without steam, you are advanced during your last visit to factory.
Yeah, so those things have, the handbook also actually provides some guidance. I was just curious to see what they're thinking about. So you understand my question, right? You apply pre-stress. So if I'm putting a beam, so here's the beam section. Let's say if I put pre-stress here, and when I release it, the beam is going to be like this. Oops. right? So you have some upward deflection here. That's what the camber is, but we are referring to, right? Now, you're going to get some additional load comes in. It could be dead load from slab, service load, and the beams comes back to this. It's a flat beam. Right? That's possible. Yes? Because I put the load, if I'm starting flat, put a load, it's going to go deflect downwards. But if I start with a camber, if I put a load, it can stay with an upward deflection, it can be flat or it can go down. All three are possible, depending on the amount of prestressing you put in. But my question is, what's the advantage if I keep it flat? What stresses do you think it's in the beam if I keep it flat? So this is going to be, this is compression, right? Sorry, that's tension. This is compression, right? But when I load it, it happens the opposite. You're going to have compression here and tension there, right? So basically, if I'm coming from here to here, I'm counterbalancing that tension with this compression with this tension. So if I do that, basically if the beam is staying flat, the beam only has axial compression. It doesn't have anything else. You see that? So if you have only axial compression, imagine designing a beam with the loads, but it's only have axial compression. There's no way it's going to crack because it's an axial compression. So you could actually design prestressed members to do that. So typically floor slabs are done in that manner. Yeah. So advantage is that if it's flat, obviously you don't have to deal with upward or downward deflection. That's another benefit. It stays compression, so it doesn't see any tension, so it's not going to crack, it's not going to leak. You get rid of a lot of problem. So that's why the camber is important. You understand and account for in terms of your benefit. Some people choose to have small upward deflection. Some people allow to have small downward deflection. There's going to be cost associated with that, but you want to pick the best option for you. We are looking at a short term. Over time, it's going to change as well. So the long-term camber should also be paid attention in terms of how you would account for. Looks like you're hungry and don't have energy. This is my last slide. Compression members. Compression members, it's like columns. I've talked to you about the axial load moment diagram that you should use. The guidelines provide guidance in terms of how you would pick the sections and the size of the sections, the amount of pre-stressing based on the load that you're looking at. And I also added that I've just covered general scenarios, right? So hopefully you got some understanding and appreciation for what happens beyond the structural design you complete. Or if you are on the side where you're going to be designing it for a precast structures, how you can take advantage of the handbook. The one thing I want you to realize is uniqueness of the structure is going to bring in some other challenges like this, and that's something you should pay attention to. In fact, the handbook also provides some other scenarios that you should account for. So as a designer, you should pay attention in terms of the sequence of construction, how it's being erected, what loads the beam is seeing. So when you do actual design, you're looking at live load, dead load, snow load, and things like that. But the construction brings in additional loads that you need to pay attention as well. And erector may say, hey, I'm going to do the construction this way, which is not outside of what you thought about. You need to make sure that you think through, will it introduce additional load? Will it introduce eccentric load? Will it introduce torsional loads? Those things is something that you have to pay attention to make sure. So precast side of things is not anything new, but understanding the sequence, identifying the potential scenarios, applying the knowledge of structural engineering, the concrete knowledge, and the pre-stressing knowledge to make sure that you don't create a situation where beam can fail, crack, deflect more permanently, things of that nature. That's what you want to prevent it. Any questions?
Wouldn't it always be beneficial to have somewhat comfort connection in the member, provided that the member satisfies those limits and all? You said that it is beneficial to have that section, that member, but wouldn't it be beneficial to have a member with slight upward inflection?
Benefit, you said?
I think wouldn't it be beneficial to have always have a member to have an upward?
Sure, yeah. So it's a scenario based, right? So it's possible. Again, that gets determined by the length, the span length, the amount of pre-stressing, the cost associated with it, and all that stuff, right? But ideally, keeping it flat keeps everything compression, right? So if I go this one, I have tension develop at the top potentially.
Provided that tension is within that.
Yeah.
It will be beneficial.
Right, but when you keep that flat, there are, even in the design calculation, you will find that it's much easier to do the calculations as well, because you are basically dealing with an axially loaded member receiving some additional loads, right? On floor slab, at least it used to be that designers prefer to do that calculation accordingly. Yeah, sure, if whatever the reason, in fact, the opposite also I've seen, they allow some deflections as long as it doesn't crack, and if it's not going to see any cracks during service, there's no reason to put more pre-stressing and make it, reaching that particular scenario. Anything else, anybody? No questions from NIT, Trichy?
Again, one more point.
Yeah, I was going to ask.
Actually, SAR is what to know. Actually, it will vary based on the condition. Like, suppose it is a very long span, I need to control the difference. Yes, I can have a breakdown. That's why we do based on the condition. So you have to play between the stress and the dispersion. It's a thing.
What is the maximum length you people are not?
18 meters. Beam is 24 meters. So long beam invariably will go for top stress.
How many? 20?
24 meters.
So in terms of transportation, what's your limit?
Transportation in Delhi and up to 18 meter, I didn't find any problems.
So like a 18 meter you transport in a semi, or like a, how do you, do you need a,
18 meter throughout India, no need of any license
Okay.
or public this thing. If I go more than 18 meter, then the site is on the, just next to the highway, no problem. Otherwise, turning radius is a problem.
okay,
So based on the site condition, IIT meters I have no other way. I can come up to the gate, but I can't turn just next to the site because I should not cut the branch. So I cascade that.
oh, I see.
In Delhi, it is an open ground, I transfer.
Okay.
So depends on the condition. But more than 24 meter, officially we have to get a over dimension transport license.
You want to add anything, Professor Amula?
No, here also I feel in India also there are different construction practices. He is giving his opinion. Now, other customers may have their own.
Yeah. Yeah, so that, I mean, again, I'm just going back to the fact that the standardizing, like in the US, one of the other thing is that trucking companies are all, they unify themselves because they know what the limits are, and so they are kind of match what's requirement in terms of
So
transportation.
that what is the length?
I thought it's typically in the 10-12 meter limit. Otherwise, so you can transport longer pieces. What happens is you need to have what they call escort vehicles. Escort vehicles, so they need to be like a police escorting the
That's it. In India, it is more than 24 meters.
24.
Yeah.
Oh, I think theirs shorter. I think 12 is what I think. So that at cost. So they will try to avoid the cost, right?
That's why here we will avoid more than 24 meters.
Okay. Yeah, I don't think it's 24 meters in the US. So anything goes.
40 feet road, sir. All the turning radius with 15 meter, that is 12 to 14 meter Without checking it will turn.
Okay.
But 18 meter, the erection engineer has to see the turning radius. More than 18 means it's purely based on chance. Most of the site will not allow. Some site, if it is just next to the highway, when the railway is going straight and turning.
All right, anybody else? Any question, comments? Why don't we break for it? We don't have any, Professor Surya is not here, Virendra is not here, so I don't know if there's food, but I'll stop and see, hopefully there's food, huh? Oh, somebody coming. No, Virendra is here. I'm wrapping it up here. Okay. Sounds like you get lunch. Now, moving into, you kind of get a feel for what the precast members, how the design of members are done. The next thing is the connection design. You will have a copy of this one. This is just a paper which is published in 2010. The paper is based on a document called ACI 550, which is, I think if you look at the references, it's the second reference in this document, which is Guide to Emulating Cast-in-Place Detailing for Seismic Design of Prestressed Concrete, or precast concrete structures. What I want to emphasize here is I want to briefly talk about how the connections are established. So depending on whether you use pin connection or rigid connections, they can establish a connection accordingly. The precasters make assumptions and they will establish the connections appropriately. This document has been revised and a new version of this document will come out, I would expect, in the next year or so. So this ACI 550 is the document, so the 550 is the committee responsible for this. The 09 is the last version, so it was last published in 2019. The 1R here stands for the first revision that was completed since they published in the document. So what I wanted to show you is a couple of details, and I'll continue to do this tomorrow also. But I want to just get down to some basic information. So whether, this one initially talk about different systems that we have talked about, but I want you to look at, so this is typically in a seismic condition, you would want to establish a, what they call a rigid connection. So in this particular case, you could see that, let's see if it works. So in this particular case, what they are doing is they are basically connecting the column reinforcement and then welding it to the reinforcement coming out of the foundation, right? So in a simple sense, one could say, okay, you are establishing continuity between two reinforcement. So if that is the case that you're going to do, from a precast point of view, you should appreciate that that region should be left out where the welding has to happen, and then, so this is going back to very old days when people use details like that. So if I go back to, let's say some other type of connection. So you can see here, they are looking at establishing some kind of a lap detail, right? So basically the rebars are lapped together. The things have evolved over time, so whether one should allow it to lap in the critical region or not have changed over time. So I just want you to see what people have thought through in terms of how to establish a connection. So this is a precast member, this is a precast member, or it could be a cast in place with the rebar sticking out. You bring the column down, you're casting that joint, basically, right? So when you establish that connection, obviously this has to be temporarily supported, and until the concrete is cast and cured, which may not be always easy. But the question is, are you allowed to have splices in the region where you are expecting critical moment to develop, So those things have been resolved or looked at over time. Here you're looking at moment column frames. So you could look at how the connections are established. In this particular case, this is precast. All of the light gray is precast. The precast are seated over a small distance, over a small support length, and dark gray is basically all of the dark gray is the in situ concrete is what they're using here. I have another document which we'll distribute it maybe tomorrow or so, right? I send you a couple more papers which has a more up-to-date information on some of the connections that people are using. So when you look at these regions, you can appreciate that connections can be established. The general thinking is that if you bring the rebars together, establish some kind of a continuity, it should perform fairly well. So more and more people are starting to use these mechanical couplers. I think we also have, they have done some testing in Rookie, looking at some of the connections involving couplers. So again, this is precast. You can see this is starting to be more attractive because you have two precast members. There's no in situ concrete is involved here. All you have to do is you provide some kind of a grout to establish a continuity or continuous connection. And then what you see here is basically a coupler, where the coupler will be already built into the column. This reinforcement is already in place. This reinforcement is already in place. You lower the column into the such that the rebars goes into the socket, and then you will have access point here to grout those couplers. All you have to do is grout the couplers, and then you can establish a rigid connection, right? There are different ways people have established grouted couplers, mechanically connected couplers. I think yours is mechanically connected couplers. Different things people have done it. You could look at the same thing for a establishing frame where you bring in a T-section or T-shaped section where this is connected horizontally. Vertically, you can use the same detail I've shown here. So you could see how these connections can be established. There are requirements in terms of, so if you see the type 1, type 2 is to do with the performance of what is expected of the rebar to develop in terms of the strength matters in terms of what type of coupler, then accordingly you will have some additional requirements as well. This is called the NMB sleeves. This is a pretty popular item in the US. NMB sleeves is, I think it's developed and marketed by a company from Japan. I don't know if you use NMB sleeves here, but I think their patent has expired, so more and more companies are producing it. So they kind of specialize in terms of developing this coupler for different bar sizes. So you could see it's narrower because this can be positioned in the factory and make sure the rebar is already in. This is a little wider because that's the receiving end. You have to have some tolerance, and they count for the tolerances. So kind of everything makes sense in terms of how people can establish a connection. So you could see here is a column-to-column connection. So if I zoom in here, you could see a little bit more. So this is a precast member, this is a precast member. Typically what they will do is, this is a grout or epoxy layer that ensures continuity, that ensures everything is straight. And then these outlets and inlet will have access, they will pump. So typically they will pump from bottom. Why do you think they pump from the bottom? To push the air out. So they will pump from the bottom until the grout comes out of the top. Typically they use a pressure grout non-string pressure grout. Sometimes they will mix it with some fibers to provide strength depending on the size of the couplers. So it's a fairly standard detail people use now to do it. So when I said in the first day about they will do all of the connections after they erected the entire building, this coupling, this grouting and everything happens after the full assembly of the entire structure typically. I don't know if that's what you guys do here. Like when you do the connections, do you do as the building goes up or do you come back at the end and do the grouting?
No, sir. As and when goes, we will do the
grouting, okay. So in the US, it's typically they complete the structure and then...
Now, after your visit, we propose a system with positioner. So that will take the construction load. We are going to do the grouting at later stage. We just propose, but erection engineers are frightened.
Yeah, so that's an advantage, but you also have an advantage of, some of the weight settlement, those things takes place before you start grouting. Otherwise, you are unnecessarily putting loads into the system. So you can see now the coupler is kind of put in a different position. It's the same NMB sleeves where the coupler is put in. So you always see a question, where do you put it? Do you put it inside the foundation, inside the column, somewhere in between? That question always come up. There are a number of structures built. So these are some of the examples of structures where couplers, grouted sleeves were used. That's what you see. I have a copy of this 550 older version. I'll see if I can get that to you guys so that you have a copy of what actually the ACA version provide as well. What I want to do is I want to talk a little bit about the structural behavior because there's a lot of misunderstanding in terms of how this works and how people interpret in terms of how the implication or let's see, maybe I did the wrong thing. How people assume, okay, I've established a fixed connection, so therefore it's going to be just fine. And it's not fine. It's seen to have issues in some earthquake as well. So I want to see if I can demonstrate that to you here. I don't know how to make this. Let me try something else. Even computers are not trusting you. The AI kicks in and say, hey, what do you want me to do? So, okay, so what I want to do is I want to just look at very simple system. So let's say here's your foundation. I want to bring a column here. It's not going. Okay, so let me just start with the cantilever column. That would be a simpler thing to do. So it's not convenient to write here. So let's assume this is a cantilever column that made out of cast in place concrete. You have a rebar here, so obviously you will have a rebar going through here, and then you have a rebar on this side. And so rigid connection is used because you're applying moment or lateral moment comes in. Typically, the load comes from either wind or earthquake loads, and there are some expectation in terms of what would happen to the system depending on what load comes in here. So if I look at the bending moment, it should be obvious to you. It's going to be like that, right? So if I push on it, you know that if I push on it, oops, it keeps changing the pen. So if I push on it, I would expect, therefore, maybe there's going to be a first crack develop at the interface, and then more cracks develop here. As you keep pushing it, your flexural crack will develop, right? You've seen that already. Now, this is going to be my most critical rebar, reinforcing bar. So if I look at the strains on the rebar, let's assume that obviously in the uncracked section, strain is going to be smaller, and then it will grow. If the strain yields, or if this reinforcement yield, it's just going to go something like that. So this is basically strain, if I call this bar of 1, right? So in the uncracked section, you will have pretty smaller value, and then it will increase as you go down in the crack section. So basically I'm saying it's yielding all the way to here, so let's call it EY, and then I have a value here, let's call it EX at the foundation. Now what happens to so if I look at the rebar strain, I know what's happened to the strain all the way to this point. What happens to the strain below that point? So if I go 20 millimeter inside, what is my strain? Zero, some value, EX.
Plastic beyond will extend to some extent inside also.
Right, so, okay, so let's agree. This strain, it's not going to go to 0. It's not, doesn't know it's crossing the foundation, right? It will, so if I go inside a little bit, it will be about EX as well. So what happens is eventually the same EX has to come down to the same, we'll have the same trend because wherever EY hit, this is how it's going to come to 0 strain here. So strain penetrate all the way to that point. If the penetration, if the extended length is small, it will penetrate all the way. So the reason we leave all of this space, including the 90-degree hook, is to bring the strain back to 0. At this point, regardless of whether you did allow adequate length or not, the strain at that point is 0. So often people ignore the fact that strain actually penetrate into the adjoining member or element, right? That's an important piece. So that's known as the strain penetration. It gets ignored in finite element analysis, gets ignored in detailed analysis. But that strain penetration, so let's now look at the deflection of the member, which is going to be, it's not the most convenient place to write or draw, but so that's my deflection. This deflection is going to come from basically the deflection is tied to curvature. Curvature is tied to strain. So if I can plot the curvature, I'll do it here, which is going to have similar shape as this. So your curvature is going to be like this all the way to here. So that's going to be your curvature as a function of height. So all of this curvature, if I integrate it, it will give me some displacement, which is this. Plus what's going to happen here is, so your foundation is rigid. Even if they crack locally, you're not going to see anything outside, right? So what happens here is that because the strains are so high, there's going to be strain compatibility between the surrounding concrete and the reinforcement penetrating into the foundation. So this region here, some of this region will basically get debonded. So as it get debonded, if I so if I look at a little more closely at the interface, so here's your column is flexing, so there's a crack here at the base, there's a crack here, the rebar is going into it. There will be a gap opens up here, some delta. Because this rebar is actually, so it's not a pull out, it's not pulling out the rebar, it's basically going through the penetration effect and extending the rebar. So this delta time wherever the compression is, creates an angle here, some theta value. So the theta is pretty small, but if you have a 3-4 meter column, what you will find is that this displacement, additional displacement basically come from that penetration effects. That component could be as much as 30%. It's not small because you have a plastic strain potentially if it's an earthquake-like situation or you're trying to develop the full moment capacity, right? So when that happens, you pull this out, it's rotating, that rotation times the height of the column. So now you go back to some of the connections I've showed earlier, even if you have coupler in a critical section at the face of the column connecting to the beam or column to column, if you develop strains or moments in the higher level, the same phenomena will have to take place, right? I can actually approximate and do a very good estimate of what this displacement is, but I must account for the effect of the penetration. So the displacement is due to this curvature here, which is what we normally account for. So if you model in finite element, for example, you will actually account for this value. This value you will not account for because they don't model penetration. So your analysis results will be off by 30% because you're not accounting for it. When you don't account for the penetration effect, what happens is if you do finite element analysis, you will find the strains right underneath the foundation gets to zero pretty quickly, which is, as you should know, based on what we discussed so far, it should not be zero. It should be actually pretty high value.
Because we use continue. Because we use
Continue, exactly. And then if you want to do individual, you cannot model the bond slip accurately, right? So that's what the issue is. So people just ignore this and model, but it doesn't produce anything useful. If this is of interest, I can add a couple more papers to the list I'm giving him. Okay, so why I'm saying this is, I want to just go to one more step and say, so if I look at force versus displacement, that's my force, this is my displacement here. It's going to remain elastic, and as yielding takes place and then continue to go plastic, this number will grow pretty significantly because in this phase, your penetration is going to be pretty significant. So the component will bring up more and more displacement. So if you agree with all of that, what I said here, I don't know why it's moving, okay. If you agree with all of what I said so far, let's now look at a scenario where you're doing the exact same thing. Now you put a coupler here because of precast construction. So I bring in, this is my coming from the foundation, I'm continuing here. Again, think of it like a cantilever column so that we understand the concept and then we can adjust things accordingly. Now I do the same thing, I apply the load there. You know what the moment is going to be. So the moment is going to be increasing linearly like something like that. But if I look at the strain is actually going to be very different now. I have grown the strain, as the strain will be very identical to what you've seen before. Will come here and then maybe yield starts. But at this point, you got a lot more steel and concrete together. So your strain actually goes down to pretty smaller value right away. And it goes down locally, but then you have an interface. If you have a precast, this will open up to some extent. So there may be just one crack develop at the interface as well. So this scenario is very different from the scenario that you have for cast in place concrete. So you can't just, because you're changing the strain demand in the rebar. Now, if I have put the coupler into the foundation, then I would have done everything as before, all the way to the foundation. But I would have disturbed the strain penetration. So everything you do for cast in place, so the whole purpose of the emulative concept is to make it look like rigid connections. That's how we design. Okay, we have a discontinuity. We came up with a coupler, introduced this, and we establishing this connection. But what people overlook is you actually change the strain pattern within the section. So how it's going to crack, how it's going to spread the plasticity, how the penetration is going to take place will all be different. Depends on where you put the couplers. Or where you put, so whether you put coupler, whether you put lap splices, whether you weld, everything will alter that. So that gets overlooked quite a bit actually in seismic situations.
This strain will not come all the way to zero, right? Because still you are mobile. Probably
No, it's a smaller value is what I'm saying. So, yeah, so there's movement, so it goes, your strain demand, so this is an inelastic strain, it probably goes down like this, and then goes up, and then shoot up again, and give a strain. So this also affects your curvature quite a bit. It creates some strain here. It may not be the same as in the other scenario. You'll have some penetration, may not be the same as before. So you cannot analyze based on what the cast in place does, expect this to do the same thing. So typically when you do the testing, so one direct impact of this is going to be, when that happens, what happens is you compromise. So this is, let's say this is delta due to strain penetration. This is delta from the member. So I'll call it M. You affect this delta SP. When people do the testing in the lab, so they want to do a reference test and one with a coupler to see if precast will work, they actually push both to the same displacement because they want to see how well it performs. What happens is, if you push, you don't have this LSP, at least it's been compromised. So if I push to the same displacement, precast is actually going to give you more of delta M and less of delta SP. So when you give more of delta M, you're actually demanding higher strain in the rebar, right? So what I'm saying is, it's not rocket science, but I want to make sure that everyone follow this. But it's a pretty intriguing thing that it's once you understand it, okay, that's obvious. But if you ignore it, you're actually making a lot of mistakes. That's the reason I just wanted to talk about that a little bit before we get more and more about the connection.
Actually, because you put a coupler in the first configuration, your effective strain distribution is going to be lesser. So,
Effective strain
integrate the curvature is also going to be lesser above the column. So I would expect delta F to be lesser.
Yes, it is, but when we do the testing, so typically what we do is we build two columns, one cast in place, one precast. We test them with the same displacement because we are in the elastic region. So every time you test, you will push them to the same displacement and see which one, how they perform, right?
But indirectly, we are overstraining, which is not in reality.
Well, we are overstraining, or we are putting more strain demand. By doing that, see the consequences, right? When I do the overstrain, so if I now plot, so if, let's say I said my cast in place response was like this. It performed like this. Now, if I do a precast and put the same displacement, so I'm basically trying to match each and every displacement, I will go something like this. And it may actually fail sooner because you're overstraining it. But when people do the test, what they report, I've seen it in published papers, they will say precast is behaving better and give you better resistance. But that's not true. It's actually you're overstraining it, so you're actually compromising its ductility capacity, which may not be a negative thing because both of them have adequate displacement capacity. But I want you to remember that you're actually putting more strain demand by introducing couplers now, which may or may not be good. The other negative side is that so if you look at the crack, I think yesterday when you guys showed the pictures, it's pretty obvious. This will have a good uniformly distributed crack. So the damage, the spread of plasticity or plastification is going to be more uniform in a cast place. Here, because you put the coupler, you're going to have a crack maybe at the interface. The rest of the cracks are going to be here. And they may not be distributed much because of the strain demand, you may end up creating one or two concentrated crack, and that's about it. Which I think they have done some testing at Rookie. You can see it in the pictures as well. Maybe you should bring and show some of the picture later on, the break time, so they can see what you have done. So the point I want to make is, our goal was to force them to be similar. The detail-wise, we are establishing continuity, we are doing all of this stuff. Behavioral-wise, they're not really the same, right? So that's something you need to pay attention to. The question is, the modification you have done from a behavioral point of view, is that a concern? Is that an issue? You may run an analysis and say, okay, I would have had 150 millimeter displacement capacity, now I have 120, 110, but that's good enough. That's one way to do it. Right? That's one approach. Or if you find that that's concerning, then obviously you need to address that in the connection design. The other thing I would emphasize is, so in both cases, look at the moment demand. So this is my cast in place, this is my precast. Now precast moment actually has gone up because of straining that we are putting in, right? So let's say in the inelastic region they stay flat. So this could have gone up by some 10% value, let's say. Now, if you look at the moment profile now, one is doing this, cast in place is doing this. The precast basically doing the same thing, but except that it's reaching this. So because your plastic moment capacity is not this, I mean, this is a plastic moment capacity, but it's been shifted here. This is where the plastification takes place. So as a result, you can see your slope goes up. So the column is going to see larger shear demand now than what you assume for a cast in place situation. Right? So your shear demand has gone up. So if you design for shear reinforcement based on cast in place, you put a couplers and establish continuity, now your shear demand going up, that could potentially create a shear failure in the column. It's so much is a concern in bridge structures, people have seen it even happening. So typically it has happened in real life.
In building columns, normally the shear criteria will not govern also.
Yeah, exactly.
Reserve capacity.
Yeah, but as a designer, somebody need to understand this, right? And make sure that it's not a concern. What I'm saying is that You cannot just change and say it's going to behave like that. So you know, behavior changes. As a designer, you need to check and make sure, okay, they're changing, but it's still adequate.
So one more doubt, then that means that I have to give more filler just next to the coupler than in the coupler portion. Is it like that? Correct?
Well, if the shear is not met, obviously you have to do that, right? If the shear demand is going up and therefore you are expecting more reinforcement is required, then you have to address that. Basically, the shear demand will go up, but in a building columns, it's not going to be as critical.
No, generally they just above the coupler, shear demand is more, so I have to give more because in notion, wherever coupler is there, they will give more stirrups. But here I have to extend little more.
Right.
Above the
Well,
coupler also, correct?
yeah. Yeah, so the coupler region, they provide confinement because of stability purposes. But outside, if its shear is high, then you have to address that, right? Again, you don't need to, you can conclude it's not an issue, but my point is, we talked about design. I want you to see that as you modify, things change, right? Then you, as a designer, you recognize and you say, okay, it's still good for me, or I need to make modification in the design.
But some mechanism is getting changed, so we have to acknowledge, but whether that is within our limit or above the limit,
Yeah.
as a designer, we have to check.
Yeah, so the point I want to make is, so I picked this particular example, and in this particular example, there are a few things I want you to observe, which is not an unrealistic example. I'm putting the coupler here at the critical section. So if you have a situation where you can relocate the coupler or connections or splices outside of the critical region, if it's possible, that's one way to avoid this problem. Right?
Sir, can you come this?
No, what I'm saying is, in this particular example, having a coupler or location at the bottom of the column makes sense because you fabricate the entire member and do it. But when you do like a beam to beam connection, for example, if the coupler can be located at a less critical region where you're not going to have these issues, then it may not matter.
Can we, in the foundation, since our most of the demand is coming at the foundation, can I extend that column inside the footing like a packet, then I can do the coupler so that the confinement will be there, so that my column, again the same conventional behavior will come. Is it okay?
So if you move the column, yeah, so you're saying that move the entire column into the foundation.
That coupler position and put
Yeah,
it inside.
but then the foundation construction becomes a little more challenging, right? I mean, foundation has to have this pocket to drop the column in. You know, those are not as easy as doing a flat foundation, it's what I'm saying. Again, all of this is possible, but you need to first recognize the problem, right?
Yes.
So, the press program, I think you probably mentioned, that got started back in the, I think it started in the 90s, the first phase of it. I got involved in the third phase. They tried to do exact same thing. And then they realized that it just doesn't make sense. The challenges that come with it is, we are making the precast to behave like a cast in place. Which is a mistake, is what the group kind of came to a conclusion. So they felt like, why do we keep asking the precast to behave like a cast-in-place concrete? Why don't we look at what is precast good at, and what is that we could do better in terms of establishing the connection? So that's when what they call a jointed connection concept was established. So jointed connection concept is basically to give you some idea. So if you have a column, one simple section would be to say how we bring the columns together, but instead of using rebars, why don't I use well, there are different ways to establish a jointed connection, but one way to establish is just use a strand which is unbonded along the entire length, and then establish connections at the top and bottom of the system. So this is anchored into the foundation, anchored at the top. In between it is not bonded to the concrete. So if I push on it, what's going to happen now is this is going to just rock like this. Your strands will be going like this. Here's your second strand. There won't be any crack developing at all because your interface here can open up completely. So there's no reason to develop crack. If I can keep the strands elastic, and if I remove the load, it's just going to snap back to its original position. The crack should close completely. So if I do that, I've established a connection. I don't crack the concrete. When I remove the load, it comes back to zero displacement. I don't have penetration problem. I have nothing. Right? So you can see from the emulation to non-emulation concept. That's what I wanted you to understand or realize how that thought process came about.
Sir, when we consider the same system, since I am advocating press wherever I go, Gopal Krishnan sir, CBRA director, now he got retired. He asked me a question to convey to his doubt actually. He told that he will discuss with you. When the crack is getting opened, there is a, what he told is there is a sudden drop in the stiffness of the structure. Sudden drop and sudden, like, what you pointed is when it opens, suddenly the rigidity drops, like the structural deformation suddenly taken a spike. So
What's the difference between that and cast in place concrete? When cast in place concrete move, crack happens, you drop the stiffness by 30-40%.
Actually, I couldn't able to answer because
So if you compare the stiffness between precast jointed system.
he told, but I didn't exactly capture his point.
Okay. Yeah, but what I'm saying is that if I compare the precast detail, jointed connection, with like equal and cast in place, the only difference is the cast in place will not have concentrated crack at the base. It will have distributed crack, right? So let's say they both get jolted to the same, even an elastic displacement. You will find the stiffness of this system is actually higher than cast in place.
That time I couldn't able to answer. So what I told is, since I fully not known about the system,
Yeah.
I told is, sir, I will study and come back like that. Actually, I couldn't able to answer his question properly. But again I will reconfirm.
Yeah.
In addition to that, you also have the maybe small Prestressed also, the cable.
Yeah. So, yeah, go ahead, sir.
Which is the governing factor, is energy or displacement? Because when we go for this, we are facing this rocking action, obviously we are reducing the energy.
Okay, so yeah, it's a good question. So system like that, so let's go back to this. So when you have this system like this, as you go into the inelastic region, the reinforcing steel is experiencing inelastic strain. And that's where the hysteretic action kicks in, right? So as you go back and forth, you dissipate the energy, you develop the hysteretic actions. So if you look at some of the old textbook, what they tell you is, if you're designing a column, what they do is they take the hysteresis loop, back calculate the equivalent viscous damping, right? She learned that from my class. So you calculate the equivalent viscous damping, and then they say, okay, this structure survived because it was able to develop plastic action. They calculated the damping and said it's equivalent to 25% damping. And then they said, okay, so in the future, what we need to do is put 25% damping. But that's an integral part. The damping is an inherent piece, come up with the flexural actions that column went through. But nobody really did look at and say, what is the minimum damping I need. What they knew was 3%, 5% that inherent in this elastic structure is not sufficient. That's the assumption they made. And if you look at the plastification that happens in columns, walls, and beams, beam ends, they quantify to be in the 25 to 35% range. So traditionally, if you're going to do something, what we say is we need to put roughly 30% damping in the structure, then it will survive earthquakes. Now with this system, if you go jointed connection, what we have done is we basically separated the strength from inelastic action, right? So I could add damping externally to the system if that's what they're looking for. So if somebody need additional damping, we will provide damping in, like there are 100 other ways people have come up with how to add damping. So as I got in, so I'm going to spend more and more with the seismic detailing for one reason. A lot of the detailing that has been developed, there's been a lot of focus on seismic detailing. Most of them can be either directly applied or more so by simplifying the detail, you can actually use it for non-seismic region as well, or low seismic region, for example. So we have done wall panel tests, for example, with this detail and concluded that if the wall has 8 or 10% damping, it will survive earthquakes. It will survive earthquakes successfully. We ran 10, 12 tests and showed there's no way you can fail this one.
See, from the earthquake point of view, when we do analysis, when we do elastic analysis, we assume 5%. So we estimate our demand. But actually for a structure to survive an earthquake, you are saying, we may need about 25 to 30% damping, right? That predominantly comes from cracking that easily. Now here, you keep the pre-stressing strand elastic. How does that achieve?
Sure. No, so what I said was the 25 to 35% damping was not invented as a requirement. It was a back calculated value which was already built into it because we are classifying the movement region. So what they did was they back calculated from those tests and said if I have 25 to 35% damping, I should be able to survive because that's what we are finding. But they never said you must have, they never said if I have to add damping. So the adding damping concept came about due to base isolation, adding supplemental damping due to jointed construction. So one of the things that we investigated is that because now that we separated the response from, so what we found is system like that may have 3-4% damping through inherent in the system, which comes with it. So if you shake any of these things, they don't shake forever. They do come to rest. But when they go through motion in a dynamic fashion, there's a lot of impact takes place, right? So that impact, so if you take a ball and with a certain roughness, if you drop it, it's not going to bounce all the time. It eventually goes down to zero. We were able to calculate that amount of damping. That's in the 3-4% as well.
So rocking you say?
Yeah, just on the rocking itself.
Okay.
So we've done that. We have also done where we put like a rubber interface. It increases the damping. So instead of rock it on top of concrete, there's a high damping rubber or different at the interface. So you let it rock, you're moving it by 1-2%. It's not huge.
But we know, sir, anyhow, whatever earthquake energy which is coming inside, I am observing in terms of elastic energy in this strand. Then why the damping? I don't.
So the impact damping is there, right? Impact damping. So the impact damping. So when the earthquake comes, it's going to rock back and forth. So as it rock back and forth every time, so it's like it's the coefficient of restitution thing, right?
Energy is absorbed, sir. Remaining energy already my strain is building up in this strand, so it will absorb.
Not all of it though. I think if you calculate the energy is not, so the kinetic energy that goes in is basically comes back because you're releasing it, right? So the question is, if I built this and shake it, how long does it take to, so what we found was if I put an 8 to 10% damping, my displacement went up by like 10%. The shaking lasted another 10%. Can the structure sustain that? This system is, everything is elastic. Why can't it sustain something like that? And so when you guys were initially talking about it, I thought for low seismic region, there's no reason not to build something like that. You can build it and you can let it rock. And we've done enough tests to show that's possible. I think that's one of the paper, I think you will get a copy of it on in terms of. So what I'm saying is it was done for seismic, but in non-seismic regions, you don't need to even think about it. So the reason this was a concern up until recent time is the pre-stressing technology, right? Can you rely on the quality of pre-stressing anchorage so that you don't lose the strand? So if you lose a strand, one of the strands goes away, is obviously you lost the connection completely. Based on, I don't know, I've done a number of tests in the last 10 plus years, 10, 15 years. I never lost a complete strand. Each of the tests we probably put through maybe 20 earthquakes. Never lost a strand. We have fractured wires within a strand. 1 or 2 wires popped. That's to do with the quality of the wedge anchorage. And we also work with the company to show that, so the wedge anchorages are good, but they basically when they release it, it comes and cut the strands. It cut into it a little bit.
So that is what in our factory also, that it is getting crushed at the local. So the local it is getting failed and it is getting snapped.
So if you know of a good manufacturer who can do a different shape strand, this anchorage, we can actually avoid that problem.
Because in our factory, that
in fact, we worked with one company, then they got sold by somebody else, and funding ran out, and we moved on. But there was information published in terms of how it should be modified.
Sir, my one doubt, sir. Low seismic, I have no doubt, sir. For high seismic, what you are seeing as a disadvantage? Because I am seeing only advantage, but what is the disadvantage you are seeing when compared to conventional?
Maybe the 8 to 10% may not be adequate. You may need more additional dams.
Yeah. So okay. So if that's the case, so we have the hybrid connection concept. So this is basically a jointed connection with the unbonded post tensioning. So people did, and we have developed some dampers as well. So if that's a concern, you could move the post tensioning in the middle and then put these things a little sensitive. Okay, you can put the post tensioning in the middle and you could put rebar in here. So it only goes inside. And you can, if you want, you can also debond part of it. That's what we ended up doing. And let the two of them work together. Now you can increase the damping by 18 to 20%. So basically you have this piece, there are a number of ways to build this one. You could have this piece built into it. It's a typical couple of things, concept, imagine, except that we debond part of the rebar. The reason we debond is you don't want that strain to build up. So by debonding, you spread the strain. Yeah, and then you control how much plasticity you want out of this, and then debond accordingly. And now this is going to provide, so basically we took what the cast in place was doing, and then combined this with this one, you now increase the damping to not 25 to 35, but maybe 15 to 20, which is more than enough.
So one more question, just for everyone understanding. Suppose if I don't control the damping, my displacement will be very good, but still my structure will be safe. So that can also be allowed.
So yeah, that's also a misconception is what I'm saying. I think what we found was the increase in displacement is true, but it's not doubling or it's not increasing by 50%. It's increased by 10%, 12%. That's what we found from the analysis and testing.
Then why we need to worry about this increasing damping? So already my structure is performing good. Only 10% increase in drift.
Yeah, so in seismic region, whoever does the code will demand, like ACI right now demands 18% minimum, even for this. So these are all incorporated in the ACI, but they put in because people who serve on the committee were like the old school thought, 25, 35%. We pushed them to cut it down. We said 10, 12. They said 25. We came to
Worst
18%.
case scenario again, the strand is getting snapped. This will actually help.
I'll show you some videos. When I come, I'll show you there.
Actually, I added a seismic isolation without asking you because when movement is very high, I want to reduce the movement, so I added the isolation so that my input energy will decrease. The input energy which is coming into the structure will decrease. That's why press system plus base isolation. So
Base isolation typically are more costly.
Very possible.
Costly.
I will go for a very low rubber based thing because my press is going to be the main.
Yeah.
This will be this whatever damping you are speaking, that fellow will take care
Yeah,
of
so
it.
unless you don't want the top of the structure to move. So, like the application of rubber bearings I've typically seen is for historic building. They don't want the structure to move. Hospitals make sense. Museums, you don't want things to fall. So those make sense where you put rubber bearing. Otherwise, it's expensive. The benefit is kind of integrated into the precast system. So for a precast operation point of view, so precast industry basically are getting pushed more in this direction.
My only doubt is, can I use the lowest version of base isolation with the press?
You could. It's not impossible, but you have to fine tune the system, right? Like if you're using base isolation, there's no reason to let the structure to vibrate. I would prefer that you just focus on base isolation, eliminate everything, right? If that is not an option, it seems like base isolation probably should not be the topic to begin with.
No, what happens with base isolation, the Indian scenario is, the first rubber is getting stiff now, so the moment it gets activated, all the manufacturer is telling 3 cycles to activate that one. Before the 3 cycles, my structure will get damaged. So that's why they are not allowing the base isolation.
Yeah, so one of the concerns with the base isolation is that it never been fully tested. Maybe 1 or 2 structures, maybe there's one experience in New Zealand, maybe 1 or 2 experience, but not to the full extent. And then there are some negative experience of base isolation also has happened here and there. Again, 1 or 2 examples. So conceptually, it's a great idea, but
As a question, sir, very low cost, any isolator, I'm not telling isolator, any damper with sliding things, rubber based, that initial friction or initial stiffness which they are speaking, rubber, when it goes for 11, 20, 40 years, it will get stiffened. So the initial cycle, it will be stiff enough, so by the time the earthquake will go inside and the first 3 cycle damage, damage will have caused. So that time I thought of having a trade between this one and the low cost isolators. Like that I thought, but is it okay or we can go for something?
I don't know, it seems like it's more work and more cost, like when you bring 2 different techniques, it becomes more challenging.
Okay. So either you
I would
go for
probably,
base isolation or not.
Yeah, if it's if it's a structure is or content is more valuable, then I would just use something like a lead rubber bearing and go full swing and make it happen.
Okay.
If that's what you're looking
But
target.
initial 3 cycles they are telling us that
So that
how to activate that rubber?
I don't know. I don't believe that. So Caltrans typically do testing on isolation or like what they call these control devices. So they pull the device from bridges and take it to the test site and test them for the reasons like they have friction pendulum. So do they perform 10 years later to the extent they were imagining it should perform? There have been some stuff done.
Oh, that 3 cycle is not mandatory, you say.
I don't believe, but people have studied that somewhat.
Because whatever test report I received, sir, 3 cycle they are giving, then only they started testing. They are giving the 3 cycle to
That's kind of cheating.
Actually, Mayes are also very concerned about that. He is saying that lead rubber means I have this concern like that he was telling.
Yeah, so like base isolation structures, the negative things. There was a bridge in New Zealand where they didn't secure the base isolation adequately in the vertical direction. So when the vertical direction motion came in, the superstructure was airlifted the isolation bent outside. It just landed on top of the pier. And then it was kind of, going, so that happened. One case where the structure has to move, so they have to have the gaps around the structure, right, as an isolation gap.
Yeah.
That was filled with dirt, basically, because nothing happened for 20 years.
Okay.
So there are things like that can potentially cause issues. But you have to take precaution on those issues.
So how much can we do for design basis earthquake? I can design the steel, and maximum concerned earthquake I can use the.
Possibly, yeah, possibly.
That's what I think.
Yeah.
Now Indian code has doubled the factor.
30%.
Yeah.
They doubled the sir.
Where is Virendra?
They
Okay.
taken up 2 also.
So the point I want to make here is that this connection, when you start thinking about it, the two direction to go, right? We said the paper that I shared with you, what they call an emulation. Their claim is they're emulating. So when they say emulating, they are basically creating the rigidity or rigid connection. But what they're not referring to, or what they're not paying attention to it is the behavioral change that you need to understand and appreciate. The second concept that I presented is what's known as a jointed connection. Be taking advantage of the features of the precast. What is best for what we know where the joint is, and we would allow it to develop gaps right at that location where the actual disturbance between the continuity from foundation to the column, for example. But that's going to behave differently, but it's actually going to be more suited for, I can't take this and put it into the cast in place. And, but we were willing to do the other way around before. So this concept got developed because the jointed connections allows you to bring in newer ideas together. And I'll present some of the things moving forward, but several of those connections can be simplified for even if you don't have seismic loading. The key here is making sure the technology, the quality control aspects in terms of the strand quality, and so if you want to do any testing, you should just test the strand, for fatigue, for anchorage, things like that you want to evaluate. If they are performing well, so we've done a series of tests on this wedge issue, cutting into the strands, can they keep multiple loads? What's that? Yeah, in
All of failure, the strand got cut, it snapped and hit the 14 meter.
well, but that's where the quality control has to come in. So in the US, we work with a number of companies. This is Dividag, VSL, CCL. They all up their game in terms of quality of the products. I don't believe, I think as I said, I never experienced, I've probably used, hundreds of anchorages like that. Never had any issue with it. Losing the strands completely. But that is the key. So if you're going to put quality control issues into these connections, that needs to be made sure. The other concern that came about, there are some people had some concern in case it breaks. Okay, we do every due diligence, but if you start using in a broad sense, what will happen if a strand breaks in one case? So there are 1 or 2 cases. What they have done is they would partially bond the strands, which is also fine. So they will go and bond portion of it with grout on top of doing the anchorage, so that if it breaks, you don't lose the strand significantly right away. So the things like that, people can take precaution.
Anyhow, the strain distribution that unbonded is, you will allow the strain distribution to a longer distance. But as we know, the strain distribution, that much height is not needed. So can we?
You could. So the goal here is to keep the strands elastic, right, up to a fairly large displacement. So you back calculate based on how much displacement is needed, and you need to have a threshold value, because during the lateral movement, the strand is going to stretch more. So say you have a target displacement of, at the design level, maximum considered earthquake, you make a decision. So typically what we do is, the way it's written is that at the design level, we keep the strands elastic. when it goes to the ultimate or the maximum considered moment, you you allow some inelastic strain to develop. So, and we also found that if you lose pre-stressing by 10%, 12%, it's okay. If you lose more, then you come back, your system is pretty sloppy because you lost the initial pre-stressing.
My question is not that instead of leaving unbound, can we increase the bond length? Anyhow, that much strain distribution is not needed. So can we?
You can.
Storage here, what is there? Can I? The strain distribution will be.
Yeah, the more strain distribution you will have, the less amount of strand you will need, because your initial elastic stress can be higher, right? Because the more you can distribute it. You understand that? So if I have, let's say this is how the stress strain curve of the strand, let's say. If this is my initial stress. If I have a long inelastic strain, it's going to go from here to here. But, so let's say this is my threshold, so I'm below threshold. But if you bond more of it, then you're going to increase, the change in strain is going to be high, then your initial strain has to be somewhere here. That means you will need more strands because your initial stress on the strands is limited. And then you have a target force for pre-stressing, right? So you will end up putting more strands. So it's like you're chasing your own tail while you could get it right from the system. Questions? You guys want to say or come and show your picture or? Huh? Based on what you heard, what do you think now in terms of?
It is like here, we go for this kind of direct connections, it's completely different. We are using the shear area, right? So, like now we are addressing that through the pre-tension or post-tension, but still we are losing the shear area. So that is the advantage of one of the things. So that we are losing, and immediately the crack opens because it is interface.
Yeah, but your pictures also show concentrated cracking, right?
Yeah, yes, but still that has second advantages, like I can even delay that. Whereas in the very beginning it is coming up. So anyway, like even if you use grout, immediately it is opening up in this case.
Sir, but here shear, diagonal shear, no need to worry. Here shear friction will come. So loss of contact is no.
No, yes.
What's the time? What's a 350?
Suppose you are not using pre-tension.
Somebody else is coming, right? Somebody else is teaching next session. Is he here?
Yeah, he's going to cover a couple of.
No, but schedule for somebody else, right?
In fact, I was supposed to cover that last thing, but I have another meeting.
Oh, so maybe, okay.
The seismic issues, we can postpone it till.
Yeah, I'm going to, The reason I talked about this is I wanted to understand the differences between the cast in place, the emulation, and what is the non-emulated. So the paper, what I want you to do, I'm supposed to give you some tutoring or tutorial. I want you to read that paper and bring up any questions you may have. We can discuss that tomorrow. Because hopefully you'll understand as you read through the paper. I want you to reflect back on the fact that by putting the location of couplers or rebars or whatnot, does it going to alter the behavior? You see that in one of the detail I've shown, they are putting lap. So when you put a lap splice, the area becomes more, you get more steel in that area. Anything you put in, it causes some issue. Lap splices also tend to try to break away, so it tend to dilate, it weakens the connection. Again, it makes sure that conceptually it matches what cast in place is supposed to do, but behaviorally it's not going to be the same, right? So the reason I got into it is, so the two reasons I wanted to understand these things, and then I want to emphasize more and more, there has been a lot of development in seismic can be brought back to So especially it's more valuable in India. It's becoming more and more, your seismic zone is shifting more towards south, right? So in a low seismic region, these details are much simpler and provide some additional protection even for a low seismic case, instead of going through other complicated. So precasters actually love these connections. If you can do it with a pre-stressing elastic connections like that. But code in the US ACI has now acknowledged the 319. It will be brought back again as acceptable connections. But the industry, when I say industry, the owners are still pretty reluctant because they are looking for somebody to build and that building to go through earthquake. That might take another 20 years or 40 years, right?
Why you are recommending press only to low seismic? It is good for.
No. Definitely for seismic, we'll talk a lot more about it. But what I'm saying is those details can have advantages rather than trying to put couplers and, right? You could use this same system with a simplified manner because it's got a lot of benefits too. Any other questions, comments? No, go ahead.
The impact between column and footing, you are applying grout or any epoxy kind of thing. So if it is exposed to elevated temperature, so the degradation will happen.
You're talking about grout in the couplers or at the interface, you're saying?
Yeah, intact between the column.
Okay.
So if it is exposed to elevated temperature, the degradation will happen.
Elevated temperatures.
So when we say epoxy modified ground, well, like a cement.
Yeah.
It's like cement.
No, we are using cementitious, nothing. Even it happens only wearing. Concrete to concrete, anyhow it will wear.
Why would that affect only the interface? It will affect the. Yeah, it's not a easily flammable material.
No, I think he misunderstood that as the epoxy that we use in FRPs.
Oh, no.
It's a cement base.
Right?
It's a cement base, cementitious. It's all, everything is cementitious.
So even though if it cracks once, whenever subject is loaded, that's something.
Crack where? Within the interface? So typically those grout pads are made out of non-shrink fiber reinforced grout material. So they typically use a fiber reinforced mixture in there. So when it hits, like if you end up say rocking for example, it will not, even if it crack, it won't break away. That's the reason they use fibers to prevent.
So again, the corrosion issue will be there. So once it cracks, the chlorides and it will penetrate to the again the corrosion issue.
Yeah, so when I say fiber, typically they don't put metallic fiber in the region. Those ones are non-metallic fiber, so it's not an issue typically. You have more problem if you don't put fibers because, as you said, during the rocking it can just crack and start shrinking. Once the contact area shrinks, your movement capacity will go down because your lever arm reduces. Question? No questions? So next time when I see you, I'll ask you about strain penetration. Right? All right, I'll stop here then.